Welcome back. Our next learning module is on control structures. We're going to be learning about relational and logical operators, how we can use those to compose simple and more complicated if statements, and then also how to do switch statements in C with some examples along the way. Looking at what we know so far, what we've learned so far in the course, we know how to assign variables, how to provide some mathematical operations on those variables, how to read in data, how to print out data. But really, so far, it's kind of a linear flow of our operations over time. On the right, we're showing what's referred to as a data flow graph. We read in a value using scanf, we do some computation on the values that we potentially read in, and then at some point we print the value back out. We would really consider that more of a calculator than a computer. Because what computers are good at, and what the term computation or computing usually implies, is some sort of data dependent decision making. And we've already kind of seen, even in the first couple of programming practice assignments, we're kind of limited in how much we can do without having more complex control flow inside our programs. So this diagram here on the left is showing an example of a so-called control and data flow graph, where it's not just this linear flow from top down of read in data, process data, spit out data. It involves some sort of data dependent decision making based on some condition either being true or being false. We determine whether or not we want to perhaps assign a certain value to a variable or perhaps some other valuable value to that other variable. And that's what I'm referring to in control structures. That is a structure we can add to our code that allows us to control the flow of the program's execution. The most basic and fundamental control structure in C is the so-called if statement, and the syntax is as follows. If, that's the keyword, in parentheses, some value we're checking to be true. If it is true, then do something. But that then do something isn't part of the syntax. If is the syntax, the parentheses is the syntax, and then we have whatever C code we need below that part for the if statement. C actually does have support for actually the true and the false keyword, but that's a very recent addition. So most example and most programs you'll see out there use as shorthand the value of 1 for true and 0 for false. Even that isn't 100% correct. I'm kind of joking by this line here, but technically 0 is false for those if statements, and anything that's non-zero is true for those if statements. So when I say if some value is true, technically there's a keyword for the truth that you can use true or false. It's defined in standard bool.h. But most commonly what we're doing is we're checking is some value non-zero or is some value 0, and that's what we're going to use to make our if statements. And to actually do that, we're going to use the so-called relational operators in C. So we already know the arithmetic operators are addition, subtraction, multiplication, division, and so on. But now we have a separate set of operators specifically for relating data to each other. That's the less than, greater than, and the other symbols that we see here on this slide. These operators return 1 if the relationship is true and 0 if the relationship is false between two values. So for example, in the less than operator there, it's exactly as you would expect it to look like. We are checking if val1 is less than val2, and we can store the result in a different variable here called result. So if we had an input where val1 is equal to 5 and val2 is equal to 4, and we were checking if val1 is less than val2 and storing the result in a variable called result, we're actually going to get a result of 0. Because in fact, val1 is not less than val2. Val1 is greater than val2. We have the greater than symbol, so we can imagine what happens here. For this relational operator, val1 is greater than val2. We would store 1 as result. There's also slightly more compound operators, less than or equal. Val1 is neither less than nor equal, so that should be 0. Greater than or equal, well, it's greater than, so that is greater than or equal. That would be a value of 1. They're not equal. There's the equal operator in C, so we get a value of 0 there. There's also then the not equal operator. That's bang equal or exclamation mark equal in C. Val1 is not equal to val2. It would return a value of result as 1. We usually don't actually assign the result as shown on the previous slide here to a variable for our relational operators. You can. This is perfectly valid syntactical C that we have here. It's much more common that we just take the relational operators, and that is what we're actually putting inside our if block in our code. So we would have, instead of setting the value of variable 1 being greater than or equal to 23 in this example, instead we were just having an if statement. If variable 1 is greater than or equal to 23, then we execute whatever within that if block. Or later on in our code, if variable 1 is greater than or equal to 64, we have another if block here that maybe does some additional processing, additional arithmetic, and then prints out the value. The strong suggestion I have for you is that you indent the code that represents the if being true. C doesn't have any white space rules, as we already saw with the obfuscated examples, and consequently, you're not required to do that in indenting. Some other languages do require a specific level of indenting for your control structures. C does not require it, but it's going to make it much easier to understand. And the requirement is that if there's more than one line of code inside the if block, you then have to use those curly braces. So the example given here is actually showing both. It's showing a single line if statement here in which we don't actually need technically the curly braces to delineate that what's inside, what should happen if this if statement is true, if variable 1 is greater than or equal to 23. And then we have an example that has two or more lines of code inside that if block, and then we do require there to be the curly braces. So when I see something's not required, but it's strongly suggested, it's a pretty common quote that people use. It's a bit violent, but assume that whoever's going to be taking a look at your code is potentially a violent psychopath who knows where you live. Well, I don't think we have to worry about there being a violent psychopath who necessarily knows where you live. I think you can maybe think of yourself as being the violent psychopath. You yourself are going to be looking at your code at some point in the future. You yourself want to be able to understand what's happening in your code. You want to follow good practices for how your code should look, because you yourself, if nobody else, are going to be looking at that code, having to understand a hour later, a day later, a week later, a year later what your code was intending. If there's no other audience for your code, you don't have to worry about me being the audience necessarily for your code. But if there's no other audience for your code, consider yourself, your future self, as an audience for your code. So this example, while perfectly correct and valid C, I would consider this to be not tremendous coding practice. So this code is exactly what was on that slide. We have a couple integer variables defined. We do our printf, scanf template here for a prompt to print out and then scanning in an integer value to be overriding a variable. We have our single line if statement. We have our multi-line bracketed if statement here. It's also, for better or for worse, quite common to see in a lot of code where if it's just a single line if statement, there's actually no new line there at all. That again, that's perfectly valid C. If we enter in, I don't know, 65 for a value that's greater than both 23 and 64, we get both the value of, yes, it's greater than or equal to 23, and because it's greater than or equal to 64, we divide it by 3, and we print out that result after the integer division by 3. This is perfectly valid. This version, that's just the single line version. This version with no tabbing at all is perfectly valid. But the reason I suggest we always want to have those curly braces, even if your if statement's only one line long, although maybe not every single example I show you will do that, but it's still my recommendation to you, is because while we look at this code, yes, today it's only one line on line 10 inside our first if statement here. You go come back to this code a week later, a month later, however long later, and you decide, oh, that's a good if statement. Actually, I'll also want to print something else off as well. This is great. Syntactically, this looks okay, right? Okay, we got our if statement with 2 lines. We got our other if statement with 2 lines. Well, what happens when we run this with the value of, let's say, 65? Hey, I tested it with the same value. Everything seems good. Same exact result or that we would expect. var1 is greater than or equal to 23. We print out this is great. var2 is equal to 21. Well, now let's print it out with 22. Can we see what's going to happen here? It's a little subtle. Prints out this is great. If you didn't have the right test case, you wouldn't have caught that happened despite this one-line code. And this is not a hypothetical example. There's been some very high-profile software bugs that are this exact example happening in code bases from very successful companies for which the engineers are well compensated and really should know better. What is actually happening in this case? Well, I mentioned if you don't have the curly braces, only the following line after the if statement is what's part of that if statement. So this code, although this is just a formatting change, what I've done here, is equivalent to the following code. And maybe in this version now we can see what's happening. We have a single line if statement. We then, independent of any if statement, have just a printf line saying this is great. And then we have our second if statement. If my intention as the programmer was to have this is great only if the variable was greater than or equal to 23, then we really should have those curly braces. And so my suggestion for you is that even if it is now a one-line printf statement, we just have the curly braces there. You decide later on, we need 2 lines or more lines. It's a very easy change to make. You're not accidentally inserting a bug when you do so. So whether we have to worry about there being a violent psychopath or not, you are potentially the violent psychopath looking at your own code there. So that's what that if statement's doing if we're looking at the controls and data flow graph. That if statement's just creating a block of code that is only executed when the relationship is true. If we want to instead have 2 branching paths, in this case we have sort of the if path. This is what happens when the relationship is true, when variable 1 is greater than or equal to 64. If we in fact want to do 2 separate things, there's 2 different ways of doing it. We can have 2 kind of opposing if statements. By that I mean we could have an if statement for if variable 1 is greater than or equal to 64, and then separately if variable 1 is less than 64, and we would guarantee that one or the other of those 2 paths would get taken. The other way to do that 2 branching paths in our code is just to use the else keyword there. By just saying else after a companion if statement, it'll take the other branching path if that condition was not true. So if it's greater than or equal to 64, we go down the left side of our control and data flow graph here. Else, if it basically was not greater than or equal to 64, that is implying very strongly that it was less than 64. We then do whatever the rest of that branch should be, and then they connect together after that if and the else block of code are both completed. We go to whatever is after that if else block, whatever is after that block of code that we have there. This is a very natural way to have control in our program. If we're doing something more than just basic calculation and we want to make some decisions based on the value of some variables, if else is a very common design that pattern we'd want to have inside our code. So while the less than, greater than, less than, greater than equal operators are reasonable and they make sense, not equal is just something you'll have to remember that it's the exclamation mark or the bang operator equal. The equal one is something that gets programmers fairly often. And I think it's understandable and very natural to conflate the equal operator in C, which is the variable assignment operator, with the equals operator, which is the equality operator, which is the one that checks if 2 values are equal. It's such a common programming mistake in C that sometimes compilers will even tell you when you're doing that, you have to tell it that that's okay, that that's what you actually want to do. In theory, that should be pretty easy to debug when this happens. And for the synthetic example that I have here, it's not that hard to tell that it happened. But in practice, this is one if statement within many, many if statements inside your program. It may work for a vast majority of your test cases. These bugs can be a little bit subtle, and this is a bug. This was presumably not the intention of a programmer to use the single equal operator versus the equals operators. Now, this IDE that we're using is pretty good. It's giving you a warning, not an error, not a compiler warning, but more of an editor warning here. The compiler won't notice it at all. And if interpreted literally, and I always tell you that they're trying to help you when they give you that suggestion, you have to kind of translate it from compiler-ese to English to really appreciate what they're trying to tell you. But it's saying using the result of an assignment as a condition without parentheses. It's kind of hard to say exactly what they mean, but it's concerned for you, is what it has there. The editor, at least, is concerned about the code that you just wrote. Can we figure out what will happen when we run this code? Printf prompt, enter in a number, read a number. If input equals 3, so not equals, if input equals 3, print out you typed in 3. Well, I'm doing my 3 check, so of course I test it with the value of 3. Looks like it's working just fine. When I type in 4 and enter that as my number, it also still prints out you typed in 3. And not only that, this is hard-coded to print out you typed in 3. If instead I actually wanted to print out the value of the input, what happens? Again, for 3, everything is as expected. Now when I do, 64, it still prints out you typed in 3. Well, what happened then in this code? That if statement is always getting taken. Why is it getting taken? Because instead of the equal equal operator, it's the assignment operator. We actually assign the value of 3 to input at this point on line 8 here in our code. Why does that return true? Well, because it's a successful assignment. And by default in C, if you have a successful variable assignment, that is a true condition that is being checked. So it's actually assigning a value of 3, and that is successful. It returns true. We always take the if statement if we now fix it as it, I guess, should be fixed. Now, only if we entered in 3 should it do so, and if we enter in 64, it shouldn't print anything out at all. We've fixed the bug. Um, it's a little annoying that it's still giving me that warning, even though we've kind of fixed the warning. We'll go back and we'll put back the warned version of it in there. It's a little unhappy. It's trying to tell you something. In general, for the code I'm providing you this semester as a starting point, it shouldn't have any little red or squiggly lines or warnings. If there are then warnings, that's a sign something isn't quite right. Whether it's an important issue or not is something that just takes some experience to discover. In this case, pretty subtle. Just by missing equal versus equal equal, you have a pretty large bug in your code. This case, it's not that hard to track down. For future cases, it might in fact be pretty hard to track down. So we can check if something is true, something is false. We have our relational operators. It's very common we want to kind of check more complex relationships between variables. For example, if we want to check if something or someone is age greater than or equal to 64 and their gender equals male. Here I use just the equal sign, well, because I'm being casual here. That's equals M in this case here. We can always do so via nesting our if statements together, nested or chained if statements. And our control and data flow graph would look something like the following. I want to do some operation, print something, do whatever, only if variable 1 is greater than equal to 64, and here at least my syntax is correct, variable 2 is equal to m, then I do some operation. If either of those conditions are false, I want to just move on, do whatever's next, whatever's in the rest of the program. That is one approach. That's nesting or chaining our if statements together. It is totally valid. There's nothing wrong with that approach. This is more of a personal preference than a very specific requirement in terms of a potential code pattern you would have here. Another approach we can use is use so-called Boolean operators to combine conditions that we're checking via our relational operators. This isn't the right syntax for it, but with our more complex relational operators, we can actually check in a single if statement if var1 is greater than or equal to 64 and var2 is equal to m. That and is exactly the sound. Both have to be true. This is true and that is true. If both are true, then we go to our left-hand side of our control flow graph. Otherwise, if either are false, we go to the rest of our program here. That and is an example of what's referred to as Boolean logic. Really, although I don't want to go too far into depth in this topic, it's really the basis of all modern digital electronics. The series of logical operators on these true and false values, and they can be combined together to make more complex both digital electronics as well as more complex relational operators in our code. In C, the Boolean operators are the 3 that are listed here. There's the and I have it as caps and here. It's ampersand is the Boolean relational and. If A is true and B is true, then that combined chained operator is true. We then have the or operator, which is exactly as it sounds. If A is true or B is true, then it's true. And then we have the invert or not logical invert operator. Not A is true only if A is itself false. And with those 3, although is defined in Boolean logic, there are quite a few other things that one can define for C programming. This is actually sufficient. With those 3, we can build really complex relational operators via just the basic less than, greater than, equal to operators we already have here. And there's a couple examples being shown here. If V1 is less than or equal to V2 and V1 is greater than V3, I recommend you say it out loud like I've been doing it. I think that's kind of important. But by saying it out loud, you're making it very clear that translation from C code to the English that you're trying to encode, the logic you're trying to encode here. In this example, if V1 is less than V2 or V1 is less than V3, that's one term. and v3 is greater than 0. Technically, our Boolean logic operators have a certain precedence order for them. My recommendation is add lots of parentheses for your code clarity. With these parentheses here, although strictly this one is not strictly required, but with these extra parentheses here, it's quite clear that this whole thing on the left-hand side is one term, and then this thing on the right side is a second term. The entire if statement itself is within a set of parentheses, and that's why you're seeing a lot of parentheses here in this example. If v1 less than v2, or v1 less than v3, and as well v3 is greater than 0, only if all that is true, then you actually take that if statement there. Let's quickly go through a couple of examples here for which of the following expressions will get taken, assuming v1 is 7, v2 is 6, and v3 is equal to 5. If v1 is less than 7, v1 is not less than 7, it's not going to get taken, it's equal to 7. If I want to check less than or equal to 7, I'd better use the less than or equal operator. Done. If v2 is not equal to v3, good, they're not equal to each other. We can also start to do some arithmetic within the if statements themselves, to the extent that's suggested and recommended versus creating a separate variable to store the sum of v2 and v3. I think if you can explain your logic to both yourself and to someone else, your logic is fine. If your logic inside your if statements is so complicated that you really can't even say it out loud and you can't even explain it to someone else, it's time to break it down a bit more. In this case, it's probably okay. If v1 is greater than v2 plus v3, v2 plus v3, I can do that in my head, is 11, v1 is 7, v1 is not greater than v2 plus v3, that doesn't get taken. Here's our first example with the Boolean operator. If v1 is less than 7 or v2 is less than 7, well, v1 is not less than 7, but v2 is less than 7, it's an or case. Or is fine, either or is another way to say that, we take that one. Here's an example of the and case. If v2 is not equal to v3 and v2 is not equal to 6, they both have to be true. Well, v2 is not equal to v3, so far so good. v2 is in fact equal to v6, so that one's not going to get taken. As an aside here, there's this concept of sort of short circuiting of the logic operations. I believe as part of the C spec, it's going to proceed from left to right inside your if statements. So if we know that the first statement is not going to be true and there's an and, the logic in your software as running on a computer won't even look at the next one. That's a bit of a micro optimization, but some programs do take advantage of that fact. Here's an example, not of the not equal operator, but of the inverse operator. This one's going to be a little bit harder to read out loud, but we'll do it slowly. If v2 equals 6 and v3 is less than v1, if that's not true, then we take this if statement. So let's see here. v2 is in fact equal to 6, and v3 is less than v1, but we got that invert here, that not operator here. So that if statement does not get taken. Even though everything else inside the if statement was true, we were checking to see if it was false. So that does not get taken here. These things can start to get pretty hairy, as I mentioned. If v1 is greater than v3 plus 1, it is. We actually don't need to look at the next one because it's an or, but this one is true. This clause here is true. v2 times v2 is greater than 40. It's not, but it doesn't really matter. This part is true. And then there's an invert again here. If it's not true, well, it is true. So that does not get taken there. The only way to learn our Boolean operators is via practice. There is no, short circuit to, no pun intended, to learning our Boolean operators. If you can explain it in English, if you can say it out in English what you are checking here, you should be able to find the equivalent C syntax for that. A little bit of trial and error is okay. How complicated you want to make your operator really depends on your tolerance for long individual lines of code versus more complicated nested and chained if statements here. There is no hard and set rule about how much complexity you add to one line of code versus breaking it up into multiple lines of code. This is a bit of a segue, but there's another set of Boolean operators in C, for better or for worse. They are similar to the Boolean relational operators for which we check and or and not. But these operators, these other operators in C, operate independently on each binary bit of the variable, the zeros and ones of the actual encoding of that variable in memory, instead of like a true false relational value here. Those are a different set of symbols, but they look really similar, and that this can be a source of frustration. And I think it's fair to be frustrated by this as a C programmer, that there's a bitwise AND operator. And we'll see an example of this. It takes the individual bits of variable A and variable B and does a logical ANDing on a bit by bit basis and stores that result as C. Same thing for the bitwise OR. There's also an XOR that checks if the bits are different from each other. And then just like there's the logical inverse, there's the bitwise NOT that inverts the bits of A and stores that result as another variable. The problem, the reason why we can sometimes be frustrated when we do this is they look kind of similar. Instead of ampersand, ampersand is just a single ampersand, and sometimes they'll basically work the same way, but not always. And so your code may work a lot of the time if you wind up using the wrong operator and then very occasionally give a long result. We could kind of write out some of the permutations of why it would sometimes give the same result and why it would sometimes give a different result. But I think it's sufficient to say that sometimes it's fine, sometimes it's not fine. We have to be very clear which one we're actually using. I can give a couple examples here. It really requires us to go back into that base 2 way of thinking like we were talking about in the prior learning module of the individual binary encoding of our variables here. So we have A and we have B, where A and B are some, in this case, maybe they'd be card types. They'd be 8-bit integer types here, and we can do the bitwise AND operation of A and B. The equivalent bit in our output C is going to be 1 only if the equivalent location in A and B are both equal to 1. So we have A, bit 0 of A is 0, so we know the result will be 0. Only in this case, when bit 1 of A is 1, bit 1 of B is 1, then the result is 1 here in bit C. Bit 2 is 0, bit 2 of B is 1, they're not both 1, so that's equal to 0 there. That's our bitwise AND operation. It's doing the same thing, it's just doing it on a bit by bit basis versus just true false values comparing. There's then the OR operator here, which is conceptually the same, except again, it's doing on a bit by bit basis. If you can determine the output here, you're in pretty good shape in terms of understanding the bitwise operators. 0 and 0, that's 0. If either of these bits are 1, the result is going to be 1 in our output here. We then have the XOR operator, for which the result in C at a given bit location will be 1 if the bit in A is different than the bit in B. So these two are the same, that's going to be a 0. These two are the same, that's going to be a 0. These two are different, these two are different, those two are going to be 1. It looks like there's going to be 3 ones and the rest are going to be zeros in that result there. And then finally, as our last bitwise Boolean example, we just invert. That's the not operator. That's that tilde character and an operator in C. The location in C is 1 if A was 0 and vice versa. We just invert the value of all those bits. You will see the bitwise Boolean operators, and you would be using them in a program really only if you have some example in which you need to grab individual bits, either obtain the value or set the value of individual bits in a variable. We're not doing a lot of that this semester. We're doing more arithmetic on our variables. But if I really wanted to determine if the 7th bit in an integer is equal to 1, there's other ways we could do that, but the bitwise operators are really intended for that. For a lot of low-level programming, that becomes an important thing. Or if I wanted to set the least significant byte of a variable to all ones, the bitwise operator would be useful for that. Let's quickly take a look at how we would do that. Both of those examples here. So this is example Boolean fun. Fun is relative, and I just get to start with, I've just kind of copied in the requirements here. So provide an expression that determines if the 7th bit is equal to 1. I guess it really depends on what we mean by the 7th bit. It's a little ambiguous. We could say that's the 7th bit starting from least significant to most significant. So we do have to then, I would say, whether we use our whiteboard, our pencil and paper, before we start coding, we have to, again, think about what the specification actually is, kind of draw inferences from there. Here we say the 7th bit, and I would just say, here's my miscellaneous thoughts, that if we have a variable with the 7th bit set to 1, I would say that that's what that corresponds to in binary. That little underscore is just to make it easier to read our bits in binary. So that's bit 1, 2, 3, 4, 5, 6, 7. That would be the 7th binary bit set to 1. In decimal, we know we can determine what that is. In decimal, that's actually 2 to the 6, and that's equal to 64. We talked about how when we're dealing with binary values, oftentimes it's a lot easier to actually think about hex digits instead because it kind of compresses that information and the conversion is straightforward. If you don't know this off the top of your head, that's perfectly fine. But in hex, that's 40 hex because there's a 4 in our first nibble here. That's 0, 1, 0, 0, and it's all zeros for the next one. That'll be useful. In terms of setting the least significant byte to all ones, that would be this, right? We'd want to set the least significant byte to all ones. It would be that we'd be setting it to. In decimal, that would be 255, something you'll very quickly remember if you don't already know that. And hex, it's FF, because all the bits are set to equal to 1. And F is 15, F is the highest value in hex. F is all the values being set to 1 here. So, okay, well, to have a code that we'd actually be testing here instead of printing out hello world, although there's nothing wrong with that, enter in a value. And this is our printf scanf loop. You're probably, getting bored with doing this in your code over and over again. Copy and paste it. In general, you'll be good to go. Declare an integer num, printing f our prompt, scanning f the actual value. We're going to check to see if the 7th bit is equal to 1. Well, it's our if statement. What would we want to check with our if statement? If the 7th bit is equal to 1, then when we do an AND operation with that value, the result should be non-zero, right? If I took that value and ANDed it with something like this, ANDed with that, the result would be 0. But if instead I ANDed with something that had something there, so this is actually a way we could potentially combine our relational operators and our bitwise booleans here. So if the value or the num logically bitwise ANDed with that value, we could do hex 40 or you could have written 64. Well, it doesn't really say to do much. The 7th bit of our value is 1. Otherwise, we can say it's not 1. It's 0 or something like that. And then for our second part here of providing an expression that sets the least significant byte to all ones, maybe we want to declare a second number that does this so we have it kind of stored for future use. This value, 255 or hex 55, is the least significant byte of all ones. If the value is then ORed with that value, let's say this value, the result would be all ones. And that's true for all of our examples we would come up with because that's how our OR operator works. Because we know one of the values has every bit being set to 1, then no matter what is in the other value, the value of num in this case, although we could have larger values as well, and we could show that as an example here as well. Let's say we have something that's more than just what would be stored in an 8-bit value. When we do that, we would certainly still have that least significant byte be all ones because we've done a logical bitwise OR with a value that is all ones already in there. So for me, I would say num2 is equal to num, and that's our logical ORing. You could do hex, you can do the decimal. You can't actually do the binary directly, but we have our hex equivalent here. And then we would want to, there is actually no printout here. The value of this with the least significant byte set to all ones is that. So here's an example where we're printing a couple things per line. The order in which we're providing those integer values after the format string matters. So the value of num with the least significant byte set to all ones is in fact num2 here. What's the example we have here? That's 48. I guess we could just test 48 for a value here. The seventh bit of 48 is 0. That's correct. And the value of 48 with the least significant byte set to all ones is 255. Well, everything that's between 0 and 255 would be 255. Let's try this. A next example here. I think it'll let me enter it in hex, although I haven't actually tried that yet. That is 13, so that's C4. Seventh bit of that is equal to 0, so it didn't let me do it as hex. That's fine. What would that be in integer here? We just do something sufficiently large. That would be fine. We just do 65, for example. Seventh bit of 65 is 1. The value of 65 is the least significant byte set to all ones is 255. And then finally, I guess to be sufficient, if we want to pick a much larger value, then let's say 512. So 512 would be a 1 followed by 8 zeros here. In this case, the seventh bit would not be 1, so that should be a 0. But now when we actually add that ORing those least significant bytes to be all ones and all digits in the least significant byte to be all ones, that would be our 512 plus our 255 value we would get back out. A couple more things I want to cover just briefly here. So we can definitely combine our multiple if-else statements in sequence, and that's what referred to as the chained or the nested block of code. There is no else-if operator in C. Some other languages actually have a separate construct called else-if, either with a space or without it, a space. You can generally implement something quite similar just by more cleverly formatting your code. That's what this diagram on the right is trying to show, a much more complex logic for code here. If your code starts to look like this, sometimes it's the time to start to think about simplifying your logic to solve a problem, but it's not that uncommon to have something with this much complexity in it. So we have our first if statement. If v1 is less than 47, we go down this if side of our control flow graph here. If it's not true, this is somewhat comparable to having an else if operator. The whole thing corresponds to else. This is like our one-line if or else statement here, but that else is then feeding into the next if. Else, we're on the right-hand side. If, now we have a new if block that is on the right-hand side of this control flow diagram. If v1 is less than 65, now we have our blocks within there. Within there, you can have chained and nested if-else blocks as well. You can generally go from this diagram to this code and conceptually go from this type of code back to this type of diagram. I don't think there's necessarily a secret to it or some quick workaround to like learning how to use if-else statements other than through practice. But this is not that uncommon. If you want to check multiple things about your data, you're going to have these either more complex relational operators or you're going to have these chained nested if statements. Which one is better than the other really depends on what you yourself can comprehend, can maybe explain to yourself and explain to others, and that you're capable of testing. It gets more difficult to test as you have more complex logic for your relational operators. You'll have to have that many more inputs to be able to show that you're actually correctly doing all the different paths within your code. And finally, the last thing I want to touch upon is the switch statement in C, because there are going to be scenarios in your code where you're going to be wanting to check the same variable over and over again. Just for example, if v1 equals 1, do something. If it equals 2, do something else. If it equals 3, do something else, etc., etc. The switch statement in C is exactly for those kind of scenarios. And I do want you to think in terms of like a dip switch versus like a light switch. It's not just on-off. It's a set of on-off values that you're really selecting based on a number. So instead of creating several sequential if statements, which is still valid and fine, you can use the switch statement to actually check for a number of different cases of an integer type variable here. So conceptually, that's what our data flow and control flow graph would look like here. Instead of a bunch of just separate if statements, you'd have just the single switch statements, and the syntax is then case. So sometimes they're referred to as switch/case statements here. You're switching on one integer variable type, and based on the value of that variable, you're going to do something if it's 1. do something else if it's 2, do something else if it's 3, etc. And then there's the syntax for the default. If it's anything else, perhaps do something else here. There's the break keyword that gets us out of the switch statement, and the default keyword, which is not always required, but it's usually good programming practice in case something else is the result of our variable that we're checking here. And you may say, well, for this variable, it's always going to be 1, 10, 15. It's never going to be anything other than 1, 10, or 15. And even if you know that and you know by design that's the case, it still is a good thing to have that default statement there. Because you know that that's the case, well, then you should throw out an error message if it ever gets to that default code. It's very easy to add a little printf error, value is not within expected range, something has gone wrong. You would then at least know a little piece of debugging information that you thought it was the case that it's only going to be 1, 10, or 5, but 15. But it turns out for this example, it's not actually just 1, 10, or 15. So the syntax is a little cumbersome, but really you can copy paste examples and format accordingly. We switch on an input, and that input has to be an integer type, of which a char type also counts. So you can switch on if the letter A or the letter B or the letter C, and that's valid because that is just an integer type encoded as an ASCII character. Can't switch on strings or on floating point values. That's just a limitation of C as a programming language. We have the switch keyword, variable name, single integer variable. We have then the case value colon syntax there, and that value must be an integer or your character type there. And then the other keyword this is introducing that we'll see in some other context, the break keyword. That's saying we've gotten to that case statement. We want to do something based on the value of the input being 10. We then want to get out of here. I'm done with my case statement. If you don't have that case statement there, and sometimes we don't want, that break statement there, and sometimes we don't want that break statement there, what would happen is we get to the value of input being 10, we would do whatever logic is right here for the input being 10, and we'll just continue down. We'll actually then do what the value would do for it being equal to 15 as well. So break is saying, I got to this point in my code, I want to get out of here. And break basically exits out of your most recent loop or switch statement. It says go from here to the end of this curly brace that we have here and get out of the switch statement. And then there's that default keyword. That is for all the other non-enumerated values here, right? For a 32-bit integer, there's 2 to the 32 possibilities you'd have to put in your case statement. I think it's fair to say that's too large of a case statement. So you should use a switch if there's a finite number of things that you're wanting to check for, where finite is not a defined thing, but there's 5 or there's 10 or there's 11 different things you're checking for. If it's 2 million things you're checking for, case statement, switch statement is not for you. But it could be the case there's a few things you're looking for, and for all other scenarios, all other values of that variable, there's something else you want to do. Then the switch statement's a pretty natural fit. It's not a requirement you use it, but it can make your code look quite clean. It's a very clear way of saying, these are the values I'm interested in. Here's what I want to do when I have those values. And finally, just to kind of summarize, I think I covered all of these. The one takeaway with switch is it may be very tempting to switch when my string is equal to Joe, or when my string is equal to Steve, or when it's equal to Carl. That doesn't work. It's got to be an integer value. So an individual character is fine, but not anything other than an int or those individual characters. The break statement is there to get out of the switch statement. I've matched a value of equal to 10. I want to get out of here. If you don't have the break statement, and that could be intentional, but if you don't have it, it'll keep executing whatever's next. That's not necessarily a bug. If you want the value for A equal to 83 and A equal to 142 to have the same functionality, you just would put them right next to each other in the case statement, and then you would just continue on through. And then the default case is optional for the functionality that isn't triggered by any of the specific cases. And it's pretty good practice to have that there, even if you personally are really, really positive that's never going to happen in my code. You still want to have it there because then at least you get a little warning message when it's not happening there in your code. Let's leave things here for right now. We're going to dig into a couple of brief examples before you get started on your programming practice, and I look forward to seeing you there.